Hiya, I'm going to go through this. This is Edexcel As paper 1. This is going to be really good revision for you if you are a full A-level student or if you're an AS student. If you're a GCSE student, I suggest this isn't the stream for you, and you go ahead and check out in the description. There's some suggested videos for you. Yesterday I ran through 2 GCSE papers, so maybe look through those, the live streams there. If you're watching this recorded, which most of you will be, I know that, then go ahead and take your time over it, okay? I'm going to go quite quickly through a lot of these questions, but pause and think to yourself, okay, what exactly do we mean by that? Take the time to read the things and think about how you would approach the questions. And whenever we go through tests like this on screen, really don't think about what the answers are, think about how we are solving the problems in front of us. Okay, that is one of the most important things, because the questions will not be the same as this. What will be the same is the types of problems that they set you and the way in which you solve the problems in front of you. Okay, just let me know that this is nice and healthy and it looks good for you. We're going to jump into the Visualiser. As I said, this is going to go quite quickly, which is fine, I think, but you need to make sure that you take your time and actually just pause the video at times and think to yourself, how did we solve that one? Okay, so here's the paper. This is the specimen paper, if you need to know, if you've done it already or anything like that. This is the specimen paper. If you wanted to try and download it and do it along with me, you're very welcome to do that. So first one, nice and easy straight off the bat. Which of the following is a vector? Well, the answer is momentum, okay. Current is not vector, it's scalar, okay. Quite a tricky one for that, but current is a magnitude of flow of charge, the rate of flow of charge. It's not necessarily a directional thing. Which is the diameter of the, what's the diameter of the coin? This is, can you read a vernier scale, basically. So the coarse scale, the first one, 1 point something, is 1.1, 1.2, 1.3. And now the next digit, so these are all 1.3s, look, the next digit is whatever one of these lines lines up with any of this scale on the vernier scale. So that's 1, 2, 3, 4, 5, 6 lines up, so 1.36, so nice easy mark there. Okay, hi Doug. I will go through some of the chat as well just at the end of the video, but I'm going to focus on the questions. So if there's one you want me to come back to, then just say, and I will do that, but at the end. Hopefully it's loud and clear, everyone, yeah? So a student carried out an experiment to measure the acceleration of freefall g. They recorded the time, so they've got t, and they recorded through a measured height, which is s, distance, space, which equation would enable the student to obtain a value for g without any additional measurements or calculations. So basically, which one of these SUVAT would enable you to work out a without having to work out the final speed, or, well, we know the initial speed is 0, so we can use this one here because it's the only one that doesn't have a v in it, and it tells you without other measurements or calculations. A small wooden sphere is held under water and released so it rises upwards towards the surface of the water. 3 forces act on the sphere: weight, upthrust and drag. Which of the following correctly shows these 3 forces when it's rising at a constant speed? So that's your 2 bits of data. It's going upwards, so drag is downwards, so it can't be either of these two. Now it's at a constant speed, so which one of these situations is the force is balanced? Well, that is A, so that's your answer there. Okay, I hope that makes sense. Next one in multiple choice. Potential difference 6 volts applied across 12 volt resistor. What's the power supplied? You can just remember these, okay. P is V squared over R and P is I squared R, because I don't think they give you those anymore in the formula sheet. I'm just double checking that. Or do they? Yeah, they don't give you them. Oh no, I'll tell a lie. They do give you this one. P is V squared over R, and there's I squared R there as well. So you do get given them in the formula sheet, but essentially power is IV, but then we derive them to make V squared over R and I squared R. So basically just make sure we get the numbers in the right place. 6 squared over 12 and gives you 3 watts. Okay, electric current in a circuit can be considered to be a rate of flow of charge. This is the definition. It's not energy transferred by unit of time. It's not the total charge flowing. It's not the work done per unit of charge. That's the voltage. All right, moving on. Rate of flow of charge. When the light dependent resistor is illuminated, its resistance falls. Okay, the light dependent resistor is connected in series with a fixed resistor. So, we're spotting this straight away, aren't we? We're thinking potential divider. Okay, this is a potential divider question. Which of the circuits would produce the greatest output in V out? Right, so basically the potential difference is shared in the ratio of the two resistances. So we can just think about it like that. But in this case, this resistance would fall and this would be fixed. So yeah, that would increase, but this would still be way larger than this. So it's not going to be this one. This resistance, yeah, this makes sense. This resistance falls, so the ratio is larger here and smaller there. So it's the right direction, and it's the larger than this one. So we're thinking this one, and then we just double check. Now in this case, this resistance would fall, so it would have less of a share of the voltage. So not this one and not this one either. Hope that makes sense to you. That one's B. A cell of EMF and an internal resistance R is connected across a variable resistor as shown. Here we go. This is the required practical. Make sure you know your required practicals, your core practicals, whatever you want to call them in this. Make sure you know them like the back of your hand. I'm just pausing because there seems to be an issue with the live stream. I don't know whether there's something wrong with the internet here. Can you let me know if you can still see me? It still seems to be streaming from my computer, but the actual stream page seems to be down. Is it okay? Looks okay now. Okay, so I'm going to jump back into it. I apologise. So moving on. Know your required practicals. So this is the internal resistance of the cell one. You plot V and I, and you get a gradient of -R and an intercept of E. Right, so actually you could just remember that. Just really thinking about that, this is the definition of what an EMF is. It's the current times the load resistance plus the current times the internal resistance. Or in other words, the EMF is the terminal PD plus the lost volts. So we can rearrange that to give y equals mx plus c in this form here, where the gradient is -R. If we plot V on the V on the y-axis and current on the x-axis, we get R as being the gradient. So essentially, we just need to make sure that we think about what this is. The gradient is negative. Yep, that makes sense. And the y-intercept is the EMF. Moving on, three resistance, blah blah blah. Are connected in parallel across a cell. Cell has a negligible internal resistance and EMF E, right, or epsilon. Leads to so use the principle of conservation of charge to show the total resistance RT of the three resistors can be found using the expression 1 over RT equals 1 over R1 plus 1 over R2 plus 1 over R3. Now I'll just say in the specification it tells you need to know how to derive these from first principle, these equations for V, I and for resistances in series and parallel, so make sure that you can do that. So conservation of charge states that, and yeah, that's where you have to start for this one to get the first mark, because it tells you to use the principle of conservation of charge. It states that the total charge into a point is equal to all the charges coming out of the point. So if you like, if you think about the charge coming in here, is just spread between these three different junctions. So from that you can say, because current is proportional to charge, this is my sort of problem solving over here, this is my step one thinking, current is proportional to charge, I can say the total current into that point is equal to the currents coming out of the points. That's actually Kirchhoff 1, so I've got myself 2 marks already. And then the last thing to do is how do you get from that into the resistances? Well, that's by Ohm's law. So this is my second little bit of thinking down here. Rearrange Ohm's law for I, gives me V over R. And so I sub all that in, and the R's are RT, the total resistance, R1, R2 and R3. And then in parallel circuits we know that the voltage is always the same in every single branch. So I can just essentially just cancel those V's and replace them with a 1. So I get this equation here. So apologies. So as I said, that's something it tells you need to derive in the spec. So make sure that you know how to do all of the all the derivations that it tells you to do in the spec, like the back of your hand, that you just do them straight away on the paper because they will come up. Okay, moving on. This is the one where it tells you on the front of the paper, it says you may need, and this is you do need, the formula sheet, ruler and a protractor. If it says you need a protractor, there's probably a question on there that you need a protractor for. And I didn't have one at home, so I printed one out. There we go. So this is me using this protractor in this question here. Now in an exam, it's an important thing to remember, if you don't have something that it tells you need on the front, ask for it, your exam centre, your school should give it to you. An airplane is flying at a constant height and speed towards an airport. At one instant, the airport is 600 kilometres away from the airplane in a direction of 60 degrees east of north. A lot of information here. The wind speed 30 metres per second acts an airplane in the direction west to east. I've just done my never reshredded week little thing around the clock face to make sure I can remember which way east is. An airplane must reach its destination in 50 minutes. So that's the time, and that is 50 times 60 seconds. Okay, so we'll just convert that when we're ready to go. Using calculation and the scaled vector diagram, determine speed and direction of the airplane relative to the air. Now, actually, I know that this is, wow, there's a whole lot of thinking to do before you get to this final answer, but you can all make sure you pick up just a mark by, you've been given a distance and you've been given a time, so work out a speed, and you actually get a mark just for working out that the speed it need to go at is 200 meters per second, making sure you convert into meters and into seconds. So you just get a mark just for doing distance over time there. Make sure that you do these things, you pick up marks where you can. Now, I've used the scale on the ruler rather than on the grid because this is printed out slightly funny scale, slightly smaller than the real thing would be. So that just bear in mind that the grid lines might not match up to what I've said I've done. So the way to think about this is as two vectors. Okay, it's the vector of the wind plus the vector of the actual distance it needs to go. Or I should say it a slightly different way. If you think about the speed and direction it needs to go to get to its destination in the right amount of time is 200 meters per second and the direction of the actual airport. So that's that first arrow there. So I've used my protractor to line up 60 degrees from north, so that's 30 degrees from the horizontal, and I've done a line which represents 200 meters per second, which I think I used 10 centimeters, right? So my scale is is half, and then I've added to that, I've added the 30 meters per second, right? So it's actually going to be blown somewhat by the wind in this direction here. So the resultant, the one it actually needs to do, is actually the difference between these two vectors. So I've drawn the line along here and measured it. It was like, well, I'll just do it quickly. It was 8.6 or 8.7 centimeters, and then I've just times that by 2 and turned it into meters per second, just done it in the same scale, and I get 175 meters per second. This is really tricky, and I know that. And then I've gone ahead and measured the angle there, which was 34 to the horizontal, and I've given it in the same way from north as they've given, so 56. That's quite a tricky one. So this is about summing vectors, and they've just phrased that in quite a difficult way. So be resilient, you can actually work these things out. Take your time and think about, all right, the speed and direction it needs to get to is the 200 meters per second in the direction of the thing, direction of the airport, but it's got a certain vector already from the wind. We just need to do the difference between them. Right, moving on. So this, earlier on, somebody asked about momentum. So here's a nice momentum question just for good practice. A child in a bumper car travelling at a velocity of 7 meters per second collides with a stationary bumper car directly ahead of them. The diagram shows the bumper cars before the collision. So assume the bumper cars move off together after the collision. Well, your first one is for just actually use of the momentum equation, and for working out the momentum before the collision is 2,100. Now they're going to collide and stick together. So this is the new mass here, 550, and I've just made that times the new speed is going to equal the same momentum as before. Now that's an important thing to get your head around. Okay, momentum before equals momentum afterwards, and that's the rule of conservation of momentum. So if you clearly show you've used conservation of momentum, you get a mark here as well. So then just lastly, rearrange for V gives me 3.82 meters per second. I strongly suggest you remember momentum in this form here, which is mass 1, initial speed 1 or initial velocity 1 plus mass 2, initial velocity 2. So in this case, the second thing wasn't moving. This was m2 over here. So I've still written in for good measure though, and then I've just worked out left hand side, right hand side, and solved. There's no kind of tricky thing there. I guess you do need to take the point that the bumper cars move off together, which means combine their mass and they've got the same speed. Okay, moving on. Calculate the magnitude of the frictional force between the cars and the floor. You're told how far they travel to come to rest, so that's a distance, it's a displacement. Now, my immediate thought was, let's go Suvat. Okay, you can do it this way, or you can do it the Suvat way. So here's the Suvat way. This is not the way they gave in the mark scheme, but it does work. So distance is 1.3, initial speed, this is after they've collided and they're moving off with this speed you've just calculated here, so you would get any error carried forward if you've used the wrong answer here. V squared equals U squared plus 2AS, with they're coming to rest, so in this case V is 0, so they're coming to rest, and I want to work out the acceleration because I've been told to work out a force, and I was thinking, I'm going to work out a force from mass times acceleration. So follow the Suvat through, input numbers, and rearrange, you get 5.5 meters per second squared. See how easy it is to make these errors. And then multiply that by the mass, which is the mass of the two things added together, which is the 550 from the last question. And you get a force which is 3053 newtons, if you like, and then that's roughly 3100. Now you do get the same answer if you go ahead and do it with the energy conservation method. So how does that work? Well, you're saying basically the kinetic energy it had is the same as the frictional work done, the work done against friction to stop it. So working out the kinetic energy, get a mark for that. Okay, and then making that equal to work done and rearranging for force, so dividing by the distance gives you 3087, which, well, rearranging was 1 mark, and then the final answer being that is 1 mark. So you did get the same thing. There is more than one way to arrive at this answer. Energy analysis is a very good way to do calculations. It's one of the most important things why we are taking such a lot of time to discuss energy at the minute in these new GCSEs and A-levels. So one assumption you've made, well, okay, that the only force basically is friction. There's no external forces on the car. You know, it doesn't have its brakes or anything. Air resistance is negligible. That's the type point. There are no external forces. It's just the friction. That's what we've assumed. Next one. Okay, this one, as I've said loads of times before, moments tend to be the easiest thing to understand and one of the trickiest things to actually do questions on. And they ask some really difficult questions on moments. So firstly though, it's an easy couple of marks though, because it's just complete the diagram by labelling the other three forces on the system. So there's 1, 2 and 3 to label. I think you'd get the marks if you did R, R and W actually. You definitely would for W because it's the same thing, but I think they'd give you it for R. But we call these normal contact forces because they are at right angles to the surfaces, so you don't need to draw those on, but just remind yourself they're contact forces produced by as a reaction to another force. Okay, use the principle of moments. This is a asterisk question, so it's a longer written question. If anyone's finding it important, I'm even going to go ahead and do a highlight on that because, oh, what'd you do there? Oh, anyway, it doesn't matter. The principle of moments, sorry, whenever you get an asterisk question, pause and think and plan slightly, okay? So use the principle of moments to explain why the system is stable in the position shown, but will topple if theta becomes too large. So actually look, I've got to my two little paragraphs I'm going to write, because the first one is use the principle of moments, and the second one is, well, what happens if theta becomes too large? So the first mark is actually just state the principle of moments really, and then the next bit is apply it to the situation. So the principle of moments states that in a closed system, the principle of moments states that a system is stable when the sum of the clockwise moments equals the sum of the anti-clockwise moments. Mark for that. Okay. In this case, the pivot is at the base of the ladder. So now I'm applying it to the situation. Currently, the weight of the system provides the anti-clockwise moment, and the normal contact force with the wall provides the clockwise moment. They are balanced, they are equal, so the ladder is balanced. So does that make sense? Here's our pivot down here. You could add to things on this if you like. These two forces are acting at the pivot, so they don't cause a moment. They are forces that are important for balancing the thing in terms of Newton's laws, but not in terms of the law of the principle of moments. Now this moment is acting to turn it clockwise. This force is acting to turn it clockwise, and this force is acting to turn it anti-clockwise. So these are the only two that we need to consider around this pivot. Okay, so what if that angle became too large? And let's imagine that. Okay, it's going to come up like this, obviously closer to the wall. Now this is the center of gravity they've marked out very carefully. So it's not just the ladder's weight or the person's weight. This is the center of gravity of the whole system. They marked that out really carefully. Now at a certain point, that is away from the ladder, so it's going to become on the right hand side of this pivot, and all of a sudden this moment is going to be clockwise as well. So that's what I put into words there basically. If the angle theta gets larger, the center of gravity of the system shifts to the right of the pivot at the base of the system. At this point, the weight of the system provides a clockwise moment and there's no anti-clockwise moment, so the ladder will topple. So now there is a resultant moment and the ladder topples. I hope that makes sense. That's a really tricky question. It's like, you almost prefer them to give you numbers at that point, wouldn't you? But you just need to think it through. What if those numbers change? What if that angle changed? How would that make the thing look? Okay, next one then. Photograph shows successive frames of a pellet being fired at a falling droplet of water. By taking measurements from the photographs, show the horizontal speed of the pellet is about 300 meters per second. Now this again is an easy question, but kids are kind of getting stuck with it. They're like, you know, this is just speed is distance over time. But kids are getting stuck with it because, you know, it's a bit like strangely worded. Take measurements from the photograph. Now again, this is a funny scale, so I've actually used the measurements they've given me, but you're told the photograph is actual size, so you can measure directly on here, you don't need to do any conversions, and you're told that the frame rate is 9,600 frames per second. And you're told it's successive frames. That means the time between this frame and that frame is 1 over 9,600. So this is the time in seconds. And you're told that you can make measurements of the distance the pellet is moving because it wants the speed of the pellet, and you can make measurements directly on there. Now what I would say is use a set square or something on this, or measure from one end of the photograph to the other end of the photograph and one end of the photograph to the other end of the photograph and do the difference between those, because you need to be to within 1 millimeter. Actually the tolerance was only 2.8 to 3.0. Okay, in this, so this is quite a, you need to be pretty darn accurate on these things. So if you use a set square from the top down, then you're going to be able to line those two things up. Anyway, so now it's just speed is distance over time, and I've cut out the middleman by doing 0.029, which is converted into meters, distance converted into meters, times by 9,600 because it's really divided by 1 over 9,600. Anyway, you get this, and it comes out, it will round to one significant figure, 300. Now that's the idea of a show that question. It means you're going to have to use this later on, and that is, so they have to give you the data, but your answer will round to this answer. Okay, to one significant figure, your answer will round. BizConsesh GCSE Business 9 to 1 is here. It's good to see you, buddy, too. I hope you're doing lots of work over the Easter as well for your classes. Anyway, let's rock on with these Edexcel AS questions, but they're useful for all exam boards. So let's rock on. The droplet fell 33 centimeters, and look, I've just quickly converted that into meters because I don't want any units coming back to haunt me later on. Before colliding with the pellet, calculate the time taken for the droplet to fall this distance. Well, the key idea is fall, and what's the secret information they haven't given you? It is acceleration is g, which is 9.81 meters per second squared. Okay, so now we can pick a suvat. We want time, we've got distance, we've got an acceleration. It starts from a speed of 0. So that's the other secret bit of information that we didn't get given, or we know. Write out the suvat, input the numbers, simplify, rearrange, and calculate. I'm sure you can all get that. So there's use of an appropriate suvat, and then it is the final answer for the 2 marks there. This one's a pretty wiggy question as well. Before the photographs were taken, the release of the droplet started a timer. After a short delay, the pellet was automatically fired, and it took 1.43 times 10 to the minus 3 seconds to reach the droplet. If the pellet is to hit the droplet, the resolution of the timer must be sufficiently small. Wow, the resolution, okay, this is not what the way we used to being asked questions about those. explain one factor that affects the size of the resolution required. So it's an explain question. I've underlined that. So think about, well, what is the factor, and then say why that matters. Why that particular factor is the factor that matters. Well, the factor that matters is the diameter of the droplet, okay, or the diameter of the pellet, because they have to collide like in space. So, you know, if the resolution is too large, okay, it's not a small enough scale, then they could miss because it could be released too early or too late. And so that's the diameter of the droplet. And the point is, if you have larger droplets, they're more likely to collide, so you don't need as big a resolution. Now, actually, you could have taken a reading of the diameter from the photograph and gone ahead and worked out what resolution that would need to be. The key thing is, I was thinking to myself, like, okay, this is you know, a question about resolution. You know, like, what's the resolution of the instrument, and you know, what affects that? Okay, well, you know, I was thinking about the actual instrument rather than the experiment. Okay, and it's the resolution required. That's what they're after. So I hope that makes sense. You know, I was trying to think to myself, well, what affects the scale of like an electronic timer? Okay, the circuitry, something like that. No, it's what affects the resolution required. One factor that affects the resolution required, which is the diameter of the pellet or the droplet. Hard question. I mean, this is tricky stuff, and a lot of people aren't going to get that, but it sorts the kind of A's from the A stars, doesn't it? A lift moves upwards from the ground to the 10th floor of the building. If you haven't tried this, then do get a physics toolbox and go up and down a lift and look at the accelerometer in your phone. Or the other one I quite like is this mass on a spring, and you can see how the force changes as you speed up and slow down in the lift. Anyway, calculate the magnitude of the maximum acceleration. So you don't need to know anything about lifts to do this. You don't need to have done that experiment. You just need to remember this is a velocity time graph and you want an acceleration. So what do? You do a gradient. So I've shown the examiner that I'm using the gradient because the first mark is use of, attempt to calculate maximum gradient, right? And I've just done a line through all of the graph along the same line that they've got there, although you could have just done a big triangle with this straight line section of the graph as well. But I always find if you do that, then the vertical dimension is nice and easy because it's the full height of the graph. And then the horizontal dimension of that triangle I've just read off 2.6 to 6.6. So delta V is 4 and T is 4 as well. Okay, so here's my acceleration is change in velocity over time, and or I could have written the gradient, and it comes out at 1, and it's two significant figures, 1.0 meters per second squared, because they've given me two significant figures on the graph. Okay, sketch the corresponding acceleration time graph on the axis below. Okay, so here's the points you need to just think, well, it's a constant acceleration for those straight line sections, so constant maximum between the first part, constant minimum between the first part there, and the rest of it, no acceleration at all. So there's no acceleration, then constant speed to 0 acceleration, then acceleration, negative acceleration, and then the same. It would have been lovely if they'd have lined this up, but you need to really read those points there as well. They weren't interested in the slope of that, they just wanted to make sure that you had a constant acceleration. Basically these two flat peaks, 3 marks, flat peak for the right duration, flat peak for the right duration, or perhaps a flat trough if you like, and 0 in between. Okay, was the 3 marks available there. Okay, moving on. Then this one again, this is a really confusing way to word some quite simple physics. Okay, so let's just think about it, pause yourself. You're going to read this and think, I've no idea how to do that, I've never seen a question like that. You're right, you've never seen a question like that. They're asking you novel questions, but how can you solve the problem? Right, by considering the forces acted on the lift, okay, that's the first thing we're going to do, is discuss the difference in the values for the power developed by the lift. So there's always that way of thinking around things. When it says discuss, you're making comparisons basically. So the first thing I've done is considered the forces. So if I've got a lift, then there's two forces acting on it, its weight and a tension, or the power, the force from the motor, if you like, pulling it upwards. It's funny, Andrew, you've retracted your message there. Thought everyone wanted to know that. I was a teenager once too, mate, so I remember that. Anyway, I'm going to crack on with the questions. By considering the forces, so here are our forces. When it's accelerating, one of these forces is larger. When it's accelerating, the tension is larger than the weight, right? Let's get a mark for that. I've considered the forces. Now during the acceleration, look, you've got greater, so this is the power when accelerating, this is the power on constant velocity, and notice these are always bigger than these. So during the acceleration, this is bigger than this. Okay, there's greater power needed for acceleration as force is proportional to power. So greater force needed from the motor, and therefore larger force is needed, larger power is needed, right? So this is the point here. Basically, tension is bigger than weight, so you need more power for the acceleration. And then, well, there's another trend here as well. There's also this 1, 2, 3. So this is my second point that I've thought about doing, and this is increasing the mass, and again, greater power is needed for more passengers as weight increases. And why? Because tension and lift must also increase, therefore power must increase as well. Because again, we've got to have, if a weight's larger and during the constant velocity, tension equals weight, then we have to increase that as well. So maybe I needed to say that in there as well, but to be honest, in the mark scheme, it just tells us we need to make sure we've considered the forces, and then we've discussed where power is greater and explained why. Okay, moving on. Lifts, and this one, another one, was just like, what on earth are they getting at? There's very few questions that are like this one in all available physics, I must admit. So lifts use a significant proportion of all total energy consumption of a building. Okay, so when designing the lift system, engineers compare, so it's a command word even though they're talking about what the engineers do, the predicted daily energy consumption of different lifts and motors by. They estimate the time for a typical lift journey. They estimate the number of lift journeys per day, and they use daily energy consumption, maximum power times number of journeys times time per journey. Discuss the advantages and disadvantages of using this method to compare the predicted energy consumption of the lift in different motors. So discuss is the key word there, right? Okay, so what I've thought to myself is, well, I'm going to talk about this point, then this point, then this point, and I'm going to say what's good about this point, what's not so good about this point, what's good about this point, not so good about this point. Okay. But in what way? Well, okay, from making a reliable, making a sure kind of estimate of the energy consumption. They've told us that the lifts make up a large proportion of all the energy consumption of the buildings. So let's see how good an estimate in these ways would be. That would be a discussion of it, wouldn't it? So firstly, my first point, estimating using speed of lift and floor numbers and heights is reliable as they are fixed values. So basically an advantage is that, okay, floor numbers and heights are quite good. However, some floors may be more regularly visited in daily use, so that's a disadvantage. So I've made the comparison though, haven't I? I've said the good thing and the bad thing. You may like to list this one as adds and then disadds. That would be a fine way to do it as well. The number of lift journeys will vary throughout the days, however, but over long periods of time this will give a reliable average of energy consumption. So there's a bad thing because they vary, but if you do it over a large period of time, then that would be fine. And actually I've done enough, and this is one of those, there's a maximum of 4 marks from a range of different points you can say. And then the last one is the equation is okay because energy is power times time, and basically number of journeys times time per journey is time. Okay, that's that question out of the way. What a wonderful question. Okay, a student is asked to determine the resistivity of a metal in the form of a wire using a graphical method. So think about that one. We need to get to a graph, and always do remember your graphs for your core practicals, for your required practicals, everyone. Okay, firstly, draw a circuit diagram and state any additional equipment that would be needed. Basically, this circuit diagram is just for making sure you've got a ammeter in series and a voltmeter in parallel. Now you could have had, with the wire being used, you could have had a ohm meter detected on in parallel with the wire being used, but if you did that, you do not need a power supply, so don't put one in. And then I've just labelled it, there's a wire being used mounted on a meter ruler. So what other equipment will they need though? Is the rest of this mark. They need a meter rule and they need a micrometer. Now you didn't need to say any of these things because they come in the next bit, but why do you need a meter rule? Because you need it to measure length. Why do you need a micrometer? Because you need it to measure diameter and then get your area. So that's what's coming in the next question. Describe how the measurements obtained could be used to determine a value for the resistivity of the metal. So this one is the equation that you get given in the formula sheet. Resistance is resistivity times length over area, this one here. So you rearrange that for rho, which is the resistivity, and that tells you your graph. So basically, remember it said to you they wanted to get a graphical method in the stem of the question. So the bit before an A, that is the stem. That means that applies to the whole question that's just coming. So we want a graph. So we're going to do dy over dx, basically. Look, so plot RA on the y-axis and L on the x-axis, and the gradient of this graph will be resistivity. So if you've got a graph that's sensible and the gradient, and you said the gradient is the important thing, then you get 2 marks there. Now it does, there's different ways of doing this. You could plot R and L on y and x, but then your gradient would be rho over A. So I find that ugly. I like to make sure when I plot my graphs that the gradient is whatever we are trying to calculate. Okay, so you could, if you did R and L, then your gradient would be rho over A. Okay, so you'd need to multiply the gradient by A to give you rho. It's valid. You can write that in there if you like, but it's same thing. What's next then? You're also going to need to measure the diameter, and you're going to need to state that you use pi r squared or pi d over 2 all squared or pi d squared over 4 to give you the cross-sectional area. Basically make sure you get there's some sensible maths in there. And you're going to vary the length, so the actual state that you're going to change the length, and you're going to measure the PD and current, and you're going to calculate resistance using Ohm's law to give resistance for each length. So you need to just go back through all your variables. If you're asked to describe a method, go back through all your variables and think, have I covered everything? Have I calculated the area? Have I calculated the resistance? Otherwise you're not going to get all those points. And one precaution the students could make to make sure the results are accurate, well, this is the one where you use a micrometer and you measure in 5 or more different points. You could say 5 points at right angles to each other as well, and calculate the average diameter. You could talk about keeping the current nice and low to ensure that you didn't get any heating effect. Okay, there's a couple of other things, or keeping the wire nice and straight, nice and taut, so that your measurement of length was accurate. But I think the most obvious one there is the measure in 5 different places to give yourself an average dimension. Now in Edexcel they have a section B, which is the synoptic question. So somebody was asking for synoptic parts as well, and this is a synoptic question here. Section B in the AS is full of synoptic questions, and in the A level then they actually have a paper 3, which is all the synoptic-y bits as well. Right. So let's move on. So a student carried out an experiment to investigate the image formed using a range of glass converging lenses. The radius of curve which at R of each lens was known. So here's a little picture. Well, we don't learn about R, do we? Okay. We don't need to know because they're going to give us some algebra that's going to allow us to work with that. So it's not something that we necessarily know about, but we can work with the algebra here. So yeah, all this stuff on waves is actually in paper 2, which we'll come on to in a minute. An object was illuminated by a light source and the position of the screen was adjusted to produce a focused image. This is the experiment here into basically ray diagrams, focal lengths V and U, etc. The distance of the lens to the screen, the image distance V, was then measured. This was repeated for lenses of different radii of curvature, so we change this lens out basically. Here's the diagram, here's the results. They've given you a blank column. They've actually told you what to calculate in this case, which is nice. And they've given you the algebra down here, which is just a slightly different form of the thin lens equation. Okay, use the grid below to plot a graph of 1 over V against 1 over R. Use the columns, so you have to draw a graph, and you have to use the columns for processed data. So let's have a look at our data. We've got 1 over R, we don't have 1 over V, so we just calculate that. And just draw your attention, this is an incredibly easy mark to lose, because you need to make sure you use the same number of significant figures as the rest of the table. So this one, these all come out as long numbers, okay? You need to round them to the same significant figures as the rest of the table, so don't lose that easy mark. And then plot your graph. Now, the marks will be for sensible scales, which means like your data has to occupy more than half the page, half the grid they give you. So make sure that you use the largest one you can do. Just think to yourself, can I double this scale? If I can't double the scale, then it's fine. Okay, so just think about it like that. You don't necessarily have to start from 0, although this one does sensibly start from 0. I couldn't double this scale though, so this is an absolutely fine thing to do, and just double check that you're going up in even scale units. Now remember your plotting accuracy as well, so really carefully using a sharp pencil, and this is the amazing mechanical pencil that keeps itself sharp as well. So I suggest mechanical pencils are the way to go, so you don't have to be sharpening, and maybe a spare one as well. This can be bought from my Amazon store as well, as can the pens that I use, if you think that you like the stationery, and the little books that we use as well. Anyway, moving back to the graph, your plotting accuracy needs to be half a small square, so be really careful. The other thing about scales is never go up in like 3s or 7s or anything like that, always 5s or 2s or 10s. So I've plotted all the data, and there's going to be a mark for the accuracy of the plotting as well, and then line of best fit, and mark for that, and look really carefully. I've got most of the points light on it, one just below it, one just above it, the rest are kind of pretty much okay. So to make sure that your line of best fits are sensible. Essentially, if they're all above it on one end or all below it on the other end, then it's not going to be the right gradient. And then the last mark is for the labels with units. Then determine a value for n. So let's go back to our bit of algebra here. Okay, it's not some algebra that we've seen before, it's purposely a bit of unknown algebra. So take your time, write the thing out, and then think about it in terms of a graph, right? What have you got where? Well, this is on my y-axis, okay, and 1 over r is on my x-axis. So what I've got, and I've just moved, the plus c across here, but we can just ignore that y-intercept down here, it's a -1, look. We can just ignore the y-intercept for now. You know pretty much it's going to be determine the gradient from these things. It might be determine a y-intercept as well, but pretty much it's going to be determine a gradient. So make sure you get yourself those marks. Anyway, so what is the gradient? Well, the gradient is n minus 1, okay, because x is 1 over r, and if you think about this as being two numbers, 1 over r times n minus 1, well that tells us what the gradient is. So in other words, this is m and that's x. Okay, so let's work out a gradient. Show the examiner that you're doing a nice large triangle. Again, look, I've gone to the edge of my page so that it's nice and easy for me to work out. I can just go 0 to this one to get my dy here, and then I read off 1.8 and 0.14 there to get dx, and I've worked out my gradient there. Comes out as 0.84 over 1.66, gives me 0.51. Now that gradient is equal to n minus 1, so add 1, in other words, to get the gradient, which is this. So again, hard mark to get exactly what n is, easy mark to show the examiner that you're using a gradient with a nice large triangle. Not as a lot of people do, a little triangle on the line somewhere, a nice large triangle. Okay, easy mark to get. And I like these questions, I like these process, there's some data, here's a bit of unknown algebra, because they're easy marks to actually get if you kind of have practiced a few of those questions. They're all pretty much the same, so they're very formulaic. They're about formulas. Right, barcode scanners, this is another tough one, right? This is some real synoptic-y stuff here. Okay, barcode scanners scan objects different distances, need a lens that changes shape, blah, 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 and focal length, blah, blah, blah. Fluid is sealed thin membrane, that's shape-changing lens, okay, got all that. Current in a coil of wire is used to change the radius or curvature of the lens. Increasing the current decreases the radius, and increases therefore the focal length of the lens, right? The manufacturer states the current in the coil should not exceed a maximum value. Justify the manufacturer's statement. Well, why on earth might the current not increase around above a maximum value? Well, actually the thing would be inaccurate at that point. Why is that? Because current causes heating. You see how there's no clues to that. That's what the bit that really annoys me about this one. The current causes heating. Well, let's go down that kind of thing. And I was thinking about electromagnetic currents, but that's in A2, isn't it? So it's not going to be that. But current causes heating. Heating leads to increased resistance because of lattice vibrations and such like that. Resistance changes the current. How does it change the current? Well, higher resistance means lower current, so that's the mark there. So basically the thing is unreliable is the kind of idea, if you exceed a maximum current. So what happens then? Well, the focal length changes because they've told you lower current, or they've told you that increasing the current increases the focal length. So focal length decreases is your final mark there. Ridiculous question. Okay, 17. A baseball bat hits a ball. Kinetic energy. Now that's a clue. That's a big clue. The ball is transferred to the bat, and the standing wave is set up along the length of the bat. So this is a question. It's all about standing waves, and is all about energy. So that's a really tricky thing to actually do this. That's what this synoptic bit is all about, is really testing out your knowledge across the whole of physics. The graph shows how the velocity of the ball impact varies with the distance of impact from the free end of the bat for two bats made of different materials. Both bats have length the same. Okay, so the hollow aluminium bat and the wooden bat. Okay, there's just some data. We're going to use that in a second, aren't we? A baseball player states it's better to use a hollow aluminium bat, hitting the ball a distance about a quarter of the length from the free end of the bat. Evaluate the player's statement. So let's look. This is a longer written question. It's not an asterisk on it though, so we don't have to worry about paragraphs, but we can still do a little bit of a plan and just plan using the question. So think, okay, first statement I'm going to make is about the hollow aluminium bat. And the second one, I'm going to talk about the length and where the person's hit it. So let's look at the two and just compare the two graphs. Aha! The hollow aluminium bat always has a higher velocity of the ball after the impact than the wooden bat does. So there's my first mark there. Velocity of the ball is always higher for the aluminium bat than the wooden bat. As the bat deforms into a standing wave, so why is that? You've got to explain why that is. This is about the standing wave. As the bat deforms, a greater percentage of elastic potential is returned as kinetic for the aluminium than for wood. So that second mark is a bit trickier. Remember, that was that clue to be talking about energy from the stem of the question. The second one is about the actual position. Now look where that peak is. It's just after the 20 mark there. It's 21 centimeters from the end of the bat. And you've been told they've both got this length here. So that is about a quarter of the way up the bat. Okay, now we've got something interesting there, haven't we? About a quarter way up the bat, we've got what we call a node. So we're going to now apply our standing waves to this explanation here. So the peak velocity for both bats is approximately 21 centimeters from the end of the bat. There's one full wavelength of a standing wave there. So that 21 centimeters is a quarter lambda. Okay, so hence there's a node there. So why might that be a good thing? Well, because nodes are points where it vibrates the least. So if you hit it right on the node, you get less vibrations. Okay, and therefore you don't waste some energy to vibrate the bat. And that's your last mark there. And you can have one more mark in this. So you could have missed any of those, because you should evaluate the statement by saying that actually, yeah, this person really knows his stuff. It's completely correct. It's best to hit it with an aluminium bat a quarter of the wavelength from the end. Okay, hard question. I'll allow that. Evaluate, but you can definitely get some of these marks because you're just picking apart the statement using the evidence that they've given you to do some justification of the statement that they've made. It might be to say the statement's a load of rubbish. That's absolutely fine. But use the evidence to evaluate the thing. Last question on this paper then. A website about the physics of baseball states, the bat hits the ball with a force equivalent to 2 tons. Okay, in a baseball game, a ball travelling 40 meters per second is in contact with the bat for 0.7 milliseconds. First thing I've done, look, is convert into SI units so that they don't come back to haunt me. With a speed of 49 meters per second. Now, what's actually happened is it started coming towards you at 40. So I've done that as minus 40. And it's left with a speed of 49 meters per second. So I've done that positive. So the difference in velocity is 89. Okay, it's an important thing just to remember. Anyway, evaluate the statement. Now they're always looking for these, and there's quite a few like that. Evaluate, justify. They're looking for a statement which is going to compare a number you've calculated with a number they've given you. So really remember that. Make that a comparative statement at the end in words. Okay, so here we are. Evaluate the statement from the website. First of all, I've found the force of 2 tons, which is just a weight basically. So mass times G. 2,000. You're told 1 ton is 1,000 kilograms. 2,000 times 9.81 gives 19,620 newtons. So that is the force that it's equivalent to, they are saying. Now the force of the ball, well, firstly we can work out the acceleration using the change in velocity over the time. So 49 minus 40 is 89 over 0.7 times 10 to the minus 3 gives you this number. Now that's the acceleration, got a mark for that. So far I've got a mark for these two. And then F equals ma. The mass of the ball is 0.15, that's the force of the thing, and then the final mark is for saying that this force is roughly equal to this force, so the statement is justified. Dudes, I hope that was helpful. That's been quite a lot of going through that. I really do hope that was helpful. I'll just there isn't much chat, I guess, because you were listening. If you're watching this recorded, then great. You can go back and sort of pause that. Is there any questions just now from those of you that have been here? Is there any questions about the questions from there that you didn't get, or was that a decent thing for you? Leave any requests for things for Friday in the description. I'm going to try my best to come back, although I think I might run out of time today. I'm going to try my best to come back and do paper 2. If I don't come back and do paper 2 today, then I will do it on Friday, the Edexcel one. And what I'll do is at the very least I'll pop up live later on, and I'll set a little date for you for paper 2. If not, then let's just look forward to that. Get on with your revision. There's loads of suggested videos if you're GCSE or A level in the descriptions. I'm Kinetic Energy, this is GCSE Physics. I hope that was helpful.